Okay, last speaker is myself. I'm rather an experimentalist on the terms of technical investigations. I built my scanning probe microscopes and I'm trying to find out how to make quantitative results. So I start with a maybe rather unusual image. Maybe some of you know about this one. This is on seafloor. Size is of about 1 meter. And the one who is responsible for it is the giant pufferfish. He built it in order to attract women. So it's something you can learn out of it. Nice, huh? Okay, go for that. You will surf for it and you can see videos in YouTube how he built it. It's quite funny. So the reason why I love this fish is because of his structure. I mean, he has a very nice surface, let's say, painting. And you will see in a second why this is interesting for me. The question is what happened, why did they invite me? And the answer is pretty easy. It's again this type of structure. And what you see here is the piezo response force microscopy image of ferroelectric domains in a yttrium manganate crystal. So this is from all three faces, X, Y, and Z phase. And it looks quite similar to the pufferfish. And the title of this paper was called Electrostatic Topology of Ferroelectric Domains. So in fact, as I told you in the beginning, I'm rather an engineering person than a deep scientist. So I feel something like misplaced here. And the question is what to do. And the answer is pretty easy. I wanted to speak about something deep in scanning probe microscopy imaging, so how to get nice results and obvious results and not plug and play with the instrument. And I realized that this makes no sense, basically. So I slightly changed my topic. I didn't change it directly to Bruegel, which with his light flowers, but I changed to scanning probe microscopy, a bouquet of possibilities for investigating samples. So what are the possibilities you have with scanning probe microscopy? Basically with even commercial scanning probe microscopes, standard AFMs, in order to investigate samples. And I will then just give an outlook on lithium niobate, which is a material I'm investigating pretty much and which has a wealth of funny effects and possibilities for nice science. Okay, I start with my booklet, and this is just a rough starting on what you can see with a scanning probe microscope. Now basically I use the AFM, the atomic force microscope. So you have a surface which you can of course image, which is a topography. So inside the surface you might have magnetic dipoles, which you can image with a magnetic tip. You can have in addition imaging electric charge distributions. I will show in detail how that works. You can measure the force directly. You can measure light by evanescent fields. And of course you can also measure the current. There's no reason why you shouldn't measure with an AFM tip the current. There's no need for a scanning probe microscope in terms of a tunneling microscope. So the main idea of all these scanning probe techniques is that you drive your interaction periodically, either the electric field or the magnetic field or the light intensity, and then you read out with different log-in amplifiers the individual signals now on the charges, on the magnetic dipoles or the evanescent fields, so on the light distribution. The big good thing here is that you can do this simultaneously. There's no reason to make one image on the electrics and then on magnetic. You can do this simultaneously since you can drive your interactions as different frequencies. Okay, I just want to start very basically on scanning force microscopy and just make you aware of a quite difficult point in terms of quantitative data. So it's pretty trivial that if you have your cantilever with the tip, then you can easily measure topography up and down and you can easily calibrate that, no doubt. If you have torsion of your cantilever, things become much more difficult because for calibrating the torsion you need to know the height of your tip. Yeah, because there's a mechanical contribution to that, and the question is how can you calibrate torsion? There's in addition a third problem is that the cantilever might also do some buckling movement if you have a force which acts along the cantilever itself. So and torsion and buckling is pretty hard to calibrate because the tip height depends on the amplitude of the signal. Even more, if you look in detail, you will find out that the vertical signal, so the up and down movement of the laser spot on your photodiode, has a contribution and from the standard deflection for topography, but also for buckling, for this in-plane deformation of the sample surface taking the tip along. Whereas the torsion, of course, is only from the lateral movement of the surface in this direction. So what can be done in order to overcome this problem? What can be done is just to rotate the sample at the position of the tip by 90 degrees, and if you rotate the sample by 90 degrees, you will transfer a buckling movement into a torsion movement. Yeah? So you need to improve your instrument in order to have a rotation stage which you can put right underneath the tip, that you don't lose the position. But this can be done. We did it. It's a little cumbersome because you have to be precise to a couple of microns, otherwise you will lose the position. But this can be done, and then you can really distinguish in between all these three forces. Okay, the next problem is the calibration issue. As I told you, for calibrating X and Y, it's pretty simple. You buy a sample. You can buy a grid or something like this, which is with high precision. It's no problem at all. If you want to calibrate the height, it's trivial too. You again buy a sample for that with perfectly defined height scales, or you can even use atomic height scales for that. So the calibrating in Z and X and Y is not difficult. The question is, how do we calibrate for torsion or buckling displacement? So how do you calibrate this movement of the tip? Even more that it depends on the length of your tip. If you ask the manufacturer of the height of your tip, it gives between 10 and 15 microns. So this is not precise enough to have a nice calibration of your system. So what I propose for that is just, and I told you I'm some sort of an engineer, is little holder, which is shown here, which has two piezo plates, identical piezo plates, which you can drive with the same frequency, with the same voltage. And you can use this piezo plate in order to calibrate this one, because this one you can calibrate on a height with the Z. The Z is calibrated of your microscope, so now you change the holder. You can calibrate this piezo plate, and if you have this one calibrated, you know that this one is pretty much the same, and you get an exact measure on how much you shifted your sample to the left or to the right. So you start with calibrating the piezo plate, and then you know exactly which is the lateral shift of your sample if you have one started with this one. This works perfectly well. And what you have to do then is to check whether the amplitude is linear with the applied voltage. So the higher the voltage, the higher is the amplitude of your lateral shift. And here what you can see is if you increase this frequency here, if you increase the frequency at a certain moment, the tip doesn't follow anymore. So you increase the frequency to more than 10 kilohertz with two large amplitudes, then the tip will not follow anymore, and it will just slide on top of the surface. If you're slow enough, the tip will follow, but if you're too fast, the tip will simply stick. So typical displacements are of the order of picometers here, lateral picometers. It's pretty precise, and with this you can really calibrate also the lateral movement of your cantilever, which might be for quantitative experiments in this case of interest. Okay, the last point is, now you can separate these movements by rotation, you can calibrate your tip, and the last thing is that you might have a crosstalk in your instrument because you have the cables or whatever pretty close to each other, and maybe the signals are not separated nicely on your segmented detector. This gives you again a mistake. And the first problem, excuse me for that, the first issue is the sample topography. So if your sample is pretty high in topography, always if you hit some bump, it will rotate a little bit. Yeah? If you scan too fast, it will rotate a little bit. So this can be overcome by slow scanning. If you scan slow enough, then this rotation won't take place. This you can easily avoid. The next thing is that you might have the cables too near to each other, which can be avoided by additional better shielding, just the cable between the vertical and the lateral movement, just the electrical cables. However, there's a third way of having a crosstalk between the lateral and the vertical signal, and this is a misalignment of the segmented photodetector with respect to the red-out laser beam. If you have your cantilever here, and you have your laser beam coming here in that way, and it oscillates this way, it gives you a plane. The laser beam defines a plane like this. Now, if you have your segmented photodetector slightly rotated with respect to this plane, you always get a torsion signal, a phantomic torsion signal, although nothing happened. Yeah, in fact, this plane should not be rotated with respect to the segmented photodetector. However, there's no way in standard microscopes to rotate the photodetector. You have no chance. So the best thing you can do is to compensate for that with a crosstalk compensator. And the answer how to do this is as follows. If you go at large distances and excite the cantilever at its resonance frequency, it should only do this movement, because this is a very low frequency with respect to this one. You just excite it at its resonance frequency and should do this. Now, if you see something in the torsion channel, this must be a photonic signal owing to the fact that there's a slight rotation of your detector. So as you can see here, we just excited the cantilever on its basic frequency 100 kilohertz, but in the horizontal channel, so in the lateral channel, we see a signal out of that, which makes no sense. The cantilever doesn't move in this direction, and you can subtract these signals electronically just by adding the anti-signal to it, right? You just add the pi shifted signal to this one, and you get a nice subtraction of this phantomic lateral signal, and you can then really clearly distinguish between vertical and lateral signals. And in addition, if you rotate once the sample, you get a clear indication on what is the answer of your sample. So the sample moves in whatever direction, or you move the tip across the sample you want to measure nicely. You have to rotate the sample, you have to make sure that they don't get a crosstalk, and then you can find out something clear about the signals. Okay, I now come to a technique which is very much used and which is not that clear in scanning probe microscopy. It's to measure electrostatic forces. So basically this is trivial. You have your sample, you have a tip which you can charge, and then you have a Coulombic force in between the tip and the sample, and that's what you can measure. How does this look like? Now, if you have a charge, let's say a positive charge in your sample, if it's positively charged your tip, you have repulsion. If it's negatively charged, you have attraction. So this is pretty trivial and nothing deep behind. However, what is interesting and not very much used is that at the double frequency, you can get an information on the conductivity of your sample. Because at the double frequency, you see the image charging in the sample. So if it's negative, the electrons will, if it's positive, the electrons will come here, and if it's negative, they will go away. So in fact, at the double frequency, you see a signature of the free charge carriers in your sample. So you can not only record the fixed charges which cannot move, but you can also record charges which are mobile inside your sample. And even more, whether they are mobile or whether they are dipoles, you can find them in the very same signal at twice the frequency. So if you have a sample, a dielectric for instance, and you're on top of it at a certain distance, you can measure the charge distribution inside your sample, whether it's fixed charging, whether it's mobile charges, or whether they are dipoles. You can distinguish between the three. However, the distinction between those two, it's not possible via frequency. You need additional information on your sample to make sure what you see. So how does this look like? This is just a bismuth silicon oxide crystal. I put a couple of corona discharges here, negative charges, positive charges, and gives a standard charge image. And the resolution in this image is of the order of 100, maybe nanometers. You can go down to a few nanometers. It's no problem at all. Now, in order to check for the mobile and the fixed charging, we prepared a special sample which are gold stripes. You can see here, and on top of it, we put some sort of a dielectric layer, just a 1-ish. And now we can apply voltage to the individual stripes. And how does this look like? It's shown here on the left-hand side. This is the fixed charge density, so the potential density. If you don't apply anything, okay, we see nothing. And the higher is the potential, the more we see a signal. Pretty nice. If you go now for the 2 omega signal, this is the signal which shows you the free charge carriers. Of course, this is copper stripes that don't care whether you apply voltage or not. So irrespective of the applied voltage, you nicely see the free charged carrier density in the 2 omega signal. Now, as a last example, I told you that you can also check for the dipoles, and for this I choose a sample, again this bismuth silicon oxide sample, which has a pretty high dielectric constant, and you see at 2 omega, which is a signal which gives you and the free charge carriers and the dielectric dipoles, you see a nice signal. So the bismuth silicon oxide has the advantage that in addition it's a photoconductor. So if you shine light on it, and that's what you see here, laser intensity, if you shine light on it, it will generate free charges inside the sample. And this is what you can see in the same sample. So this is without light, and the more you shine light in it, the more you get a signal at this 2 omega frequency, the frequency of the free charge carriers. And okay, there's some sort of a saturation now in this case at 15 watts per square centimeter. So obviously with scanning probe microscopy without any specific additional activities, you can nicely distinguish between fixed charge carriers and free charge carriers. Now, can you also use the CISPAN to really determine the surface charge carrier density? Give a real number on the surface charge carrier density. This is pretty difficult. And let's start with the problem. If you have a single charge here, small charge here, you have a charge tip, you can easily calculate the force. It's no problem at all. And you can assume that the tip is not charged and you have only charge here and everything would be okay. However, for surface charge carrier density, the situation is quite different because you have the whole surface charged. And obviously, you also get the force between the cantilever and between the cone of the tip with the surface charge density. So you can't model this system anymore. Furthermore, the next problem is what you would need is a calibration sample. And you will never find a sample which you can buy where they tell you surface charge density is so many coulomb per square meter. Makes no sense because it's wet and then it changes. Everything is pretty hard. You won't find that. And obviously a sample with a known surface charge density is simply impossible. You can't get this. What you can do, however, is to get a sample with a controllable change of the surface charge density. And this would be enough in order to quantify. So you don't need the absolute value, but you need the controllable change of the surface charge density. On all those samples are pyroelectrics. Every pyroelectric does it. A pyroelectric is defined by the idea that you change the temperature by a known amount, and this changes you the surface charge density. So if you look at with your microscope as such a pyroelectric sample, you should be able to really measure the quantity of your surface charge density in absolute values. So the experiment looks as follows. Here's your cantilever chip and the probe at the very ending. I have a pyroelectric crystal put on top of a heater. These values can be read from a data book. And the data look as follows. You have here no electrostatic force means no surface charge density, and if you change the temperature in steps of 0.5 or 2.5 Kelvin here, you see that the electrostatic force increases, and with that the surface charge carrier density increases, and you can calibrate it by these numbers because these numbers are known for macroscopic experiments. So doing experiments like this, you can really calibrate your instrument on surface charge density with the chip, with the cantilever, with the cone, with the tip. Everything is calibrated. And irrespective of whether we change the temperature in minutes or in seconds, we got pretty much the same result. So this seems stable. So these results were obtained with lithium niobate, as you can see. And we did even more measurements on the material because the surface charge density of lithium niobate is supposed to be extremely high. And we checked for that with a long-term measurement. And as you can see here, this was a measurement that lasted over 3 days. So it was somehow tricky to keep the tip sample distance constant for these 3 days, but we found a way to do so. And what you can see, we stabilized our system at 30 degrees centigrade. We changed it by 1 degree, so the surface charge density dropped by this 80 microcoulombs per square centimeter because this is the value from the data booklet, and that it recovered. So obviously the crystal wants to be charged. We proposed the crystal get rid of your surface charge density, but crystal doesn't want it like to be charged, which might be due to the polarization which is inside the crystal. Come to that in a second. So the recovering takes half a day. And you can calculate what is recovering owing to whether it's external by humidity or whether it's internal. And if you take this half a day value here, 1.7, 10 to the 4 seconds, this nicely compares with the Maxwell relaxation time given by the material. So obviously this is an internal charge density which is from the crystal inside and has nothing to do with humidity. We checked, and indeed if you may have dry atmosphere or wet atmosphere, it didn't change anything. Okay, this brings me to lithium niobate, which is the second part of my talk. I just want to promote the material because you can make lots of funny stuff with that. It has a theoretically extremely high surface charge density. The one we measured is a little lower. It has a huge Chorossy field. This is the field you need to change the direction of the polarization inside the crystal. It is pyroelectric, it is piezoelectric, it is electro-optic, and what you do standard with this material is this periodic poling, and you use it then for frequency doubling. For frequency doubling by quasi-phase matching, so these crystals can be bought, are available in commercial style, and not even expensive. So the next thing I want to show you is how can you record these domains again with scanning probe microscopy. Manu showed an image on that, and I just want to emphasize how this works. So this is our standard setup for a scanning probe microscope. Now the trick is, again, you drive an interaction periodically and you read out with a lock-in amplifier the interaction directly. So if you now have a ferroelectric sample, you apply a voltage to the tip, you get a piezo effect because ferroelectricity entails piezoelectricity. So you get a signal change inside your material, and with this, now it's shown the schematics of such a periodically poled sample, and if you scan now across the sample surface, you nicely get such a signal from a periodically poled lithium niobate, 10 micron period widths, and these two signals can be recorded simultaneously and independently. So you nicely see nearly nothing of the height waveguide, which is in topographical effect. So this is topography, and this is the piezo response of the sample. It's extremely sensitive, and the image I showed at the very beginning of this cube of the yttrium manganate, it has only piezoelectric coefficient of 0.1 picometer per volt. So taking or recording the large images is therefore quite challenging, and you could just overcome the small piezo coefficient by taking long time for scanning. Okay, I told you about electrostatic force microscopy. I just told you about piezo response force microscopy, and if you look in detail, everything is same, besides the fact that here you have a little gap, and here you have no gap in between the tip and the sample. Now, since the materials which are polarized carry a large surface polarization charge, the question is whether with piezo response do you record only the piezoelectric deformation of your sample, or do you also record the charging? Because the surface is charged, depending on the polarization, plus and minus, it carries strong charges. How can you check for this? It's pretty trivial. We measure the surface charge density in the material to be, in reality, 140 microcoulomb per square meter. For the pyroelectric coefficient, it's of the same order of magnitude. So what you can do is you record an image, and while recording the image, you cool down the sample. So we cool down the sample from 30 degrees centigrade to minus 80, and we scanned. So this is a slow scanning direction, and while we cool down, we scanned the sample. And obviously, we drastically change the surface charge density owing to the pyroelectric coefficient. However, there's no change in the contrast. So we assume that the PFM signal is not affected by any electrostatics. Okay. Now, if you can change the temperature, what you can do is while scanning again, so this is a slow scanning direction, while scanning again, we can change, now in this case, the domain in different material, it's barium titanate, and you see that it undergoes a phase transition over here, and we can come back, and the domains basically restore. It looks a little different, but they basically restore to its original shape, the patterning. So if you look inside the barium titanate, if you cool down, it's a very abrupt change of the phase from tetrahedral to orthorhombic. It's pretty abrupt. If you come back to higher temperatures, it's a slower transition, as you can see here. So everything fits nicely, and we can explain on how the domains evolved and so forth. If you really analyze those images, you're pretty sure that you know what happens inside the sample. I'm not going into detail because this needs some head gymnastics. So what I told you so far is just that with PFM and EFM you can see the domain patterning, you can see the surface charge density. It's quite fascinating. And what I want now to tell you in a short moment is, okay, you pole your sample, you have a polarization, you apply a strong electric field, you reverse the polarization, and the question is what happens at the domain wall. What is the domain wall? Does the domain wall have properties? So the domain wall is known to be of the order of few nanometers wide, few 10, something like this, few nanometers wide. And recently, a couple of years ago, it was found that they are conductive. So across the domain wall, which is the lithium niobate is a horribly insulating material, no way. But from the moment you put a domain wall in it, you can see that at the domain wall inside, at the very domain wall, you can find conductivity. So first presented in 2009 in bismuth ferrite, the same material Manu was presenting. I just show here a very elegant image of Dennis Meyer in a erbium manganate, and you see here this is a piezo response image behind, and you see here this is the conductivity at the domain walls. So recording is nothing deep, you just have your tip, you apply a voltage and you measure the current. You are in contact and you can directly measure the current going through this domain wall. So is it conductive? It's not conductive, it's less insulating. So it's always said conductive in domain wall, but it's not conducting at all. It's just, I fully admit it's less insulating, but it has nothing to do with conductivity. I will give you a couple of numbers in a second. So we measured this too, everybody does. It's the actual state, and we measured it over a couple of days, and you see that the domain is shrinking, and if it's shrinking, you nicely see that it's conducting. So the domain disappears, and at the position where the domain was before, at the domain wall, you see nice conductivity. So from a couple of different experiments, we could estimate quantitatively the conductivity, assuming a 10 nanometer wide wall, and it's 0.03 ohm centimeters. The dark conductivity of the material is 15 orders of magnitude larger, but the real material, so-called copper, a so-called conductor, is something different too. So again, I fully agree that the domain wall is less insulating than the surrounding, but it has nothing to do with conductivity. But it's not understood really what happens at the domain wall, so it makes sense to go for further investigations. So I'm coming pretty shortly to the very last part, couple of 3 slides. Again, if you have this domain structure, you can use them for nanostructuring. And this works as follows. The material etches differentially. So this is your piplin starting, and if you put it in HF for a couple of minutes, what you will see that this face edges away where this face stays unetched. Now if you want to have nice wedges here, not sharp stuff, you put it in the oven close to the Curie temperature, which is about 1200 degrees centigrades, and then we have nice smooth domain patterns. So how does this work? We start with writing domains with a force microscope. You apply the voltage, and we can make domains of different shapes on purpose. It's no problem. And then with these holes, we can make patterns like this. The are etched, they're pretty small. And you look inside, they're pretty nice. This is a classical, typical image which you just achieve once. You know this. This is the so-called typical one. Okay. So you can make nice structures. We're thinking about using those for photonic crystal devices. Okay. Other thing, I will skip this one, just to be faster. Other thing is that we can write domains also with UV light. So you have a laser beam, you can directly define the domain, you pole it, and you can make nice light guide, waveguides, rich waveguides as shown here. You can even make them like this, bridges, whatever we like. And the last part is we can make this type of tips, and if you put them in the oven, they look pretty nice. And if you put them even better in the oven, we can make some sort of, I call them photonic mushrooms. So they're pretty small, as you can see. It's of the order of 2 microns diameter, and we want to use them for whispering gallery mode resonators. So they are single crystalline, they're perfectly ferroelectric, they're perfect crystals, everything is okay. They're freestanding, as you can see, and you could couple light in either coming from here or coming from the outside. Okay, with this I want to thank the people in Bonn working with me, Southampton for the photonic mushrooms. With Osgood we did this photonic crystal stuff. And as you can see, it's a nice playground. This is a other Bruegel, it's not the same one from the flowers, yeah? Don't get mixed up with this family. But this is it's the children's games, and I think physics in these terms in lithium niobate is just big game, big fun. Thanks for listening, and I'm open for questions.